I probably didn't. Thank you. Okay, so in 7A, the here were the resistors. In the charging circuit, I go from one side of the battery to the other, and 3 and 1 and 2 and 4 were all in the charging circuit. And the discharging circuit is going from one side of the capacitor to the other, and 1 and 2 are in the discharge circuit. Okay, but not 3 and 4. And what else? I didn't put anything here, and I didn't put anything here. So I put something here, I put something here, but and I put something here, but I haven't put anything here and I haven't put anything here. So I'm going to put something here, and then keep one other one, just to make it different. So I'm going to flip this horizontally. Okay. I'm going to have something here in that part of the circuit that I didn't have before. I'm going to have let me do 2 and 3 in parallel up here. That'll be fun. And 4 I'll put here. Okay. So I'm going to have 2 and 3. I told you I like to have at least some parallel so that you remember how to do resistors in parallel. And you also have to remember that the resistors in series and parallel sort of does the opposite of the capacitors. So that's another one of the tricks of this. Okay. Okay. So here's what I have so far, and now I need the capacitors. And what did I have before? Again, I'm just trying to make it a different problem. Before I had 1 and 2 were in series, and then that combination was in parallel with 3. So I think to make it different, I'll have parallel first and then series, just to mix it up. So I'll have the one end, I'm going to rotate these all. Rotate, rotate, rotate. And I'm going to have, before I had 2 in series, and then that was in parallel. Now I'm going to do the opposite just to be different. I'm going to have these 2 in parallel. Of course, I'm telling you all the answers of the analysis as I'm making it, but that's all right. And then there is that, so I'm making it different. And then let me move this over to make room for my oscilloscope. And I like the 4-channel. There are 2 oscilloscopes over here. The oscilloscopes first are over here. And then I prefer the second one, the 4-channel one. And I'm going to connect A and then the ground to down here. Okay. And let me just change this net color to black. Okay. Any questions so far? So I just made a circuit, try to mix things up from the thing that is on lab 7A. Okay, so now we have this, the theory to do and the simulation to do. Okay, so I'll just leave it at 12. Why not? All right, so we have, I have to show some work. I'll do it by sort of like writing words in here, and I'll say that, so the charging circuit, I'm going to do the charging circuit first. And what's the path of the charging circuit? The charging circuit is the circuit that has the battery in it. So I have to move my switch up. That's the charging circuit. And I have to get from one side of the battery to the other. And so who's in there? 2 and 3 are in the charging circuit, along with 4 and the capacitors. So it's 2, 3, and 4 are in the charging circuit. And the first thing I see is 2 and 3 in parallel. So R2, R3 parallel. And resistors in parallel add reciprocally. So I don't want to be a programmer, I want to be a scientist. Okay. 1.58 and reciprocal plus 2.15 reciprocal equals to perform the addition and another reciprocal. So 0.9107, I'll say 0.9107. Okay, and then that, the R, I'll call it 2, 3, after I combine 2 and 3, that is in series with R4. And so that's just an addition. So that is 4.75 plus 0.9107 to give me 5.6607. 5.6607. Okay, has anybody been working along with me? Do you agree with my numbers? Okay, thanks. All right, so I hope that's right. We'll see. All right, so that is my equivalent resistance for going up for the charging circuit. And so if that is the answer to some question I ask, and it is, then I got to give it a unit because I don't want to lose the unit points. Okay, then what is the equivalent capacitance? That's what I have to do next. And so C1 and C2 are in parallel. There's a combination of wire on the top. There's a connection of wire on the bottom. And so that is C1 and C2 are parallel. And capacitors in parallel just add. Remember, it's the opposite math from the resistors. So that is 3.3 plus 1.6. It's 4.9. And then I'm going to take that C2, 3, or sorry, the C1, 2 combination, and that is in series with the third capacitor. And capacitors in series add reciprocally. So I'm going to do the 4.9 1 on plus the 2.4 1 on equals 1 on, and I'm getting 1.6109. Keeping lots of decimal places today. And that is an answer to what's the equivalent capacitance in the charging circuit. So I better give it a unit. It's 1.6109. Okay. Then I want to know the time constant and for the charging circuit, and that's just R times C. And so it's the equivalent R times the equivalent C. So 5.6607 times 1.6109, and I'm getting a 9112. And that's going to be kilo ohm times microfarad, and that's going to be millisecond. Okay, so it's thousands of ohms, but it's millionths of farads, and so there's still 10 to the minus 3, which is milli. And that's what I'm going to give you. I'm going to give you kilo ohms. I'm going to give you microfarads. So your answer is going to be milliseconds, unless it ends up to be, calculation wise, it'll be milliseconds. And then if it happens to be a fraction of a millisecond, then it might come up on the oscilloscope as like hundreds, like, 897 microseconds or something. We'll see. Okay, but not in this case because it's more than a millisecond. Okay. So that is the theory for charging. Let's look at discharging. When we are discharging, we are going, now the capacitors have charge, and we're going from one side of the capacitors to the other. One side of the capacitors to the other. So that's 1 and 4. 2 and 3 are out of it. It's just 1 and 4, and they are in series. To get from one side to the other, I have to pass through 4, then I have to pass through 1. Everything that passes through 4 passes through 1. They are in series. So it is R1, R4 series. That's just addition. And so that is 4.75 plus 1.65, and that's 6.4. And that's kilo ohm. And the capacitors are the same. Somebody needs to. So the capacitors are the same as in the charging circuit. So I'm just going to say to take my answer from above. And then the time constant is R times C again. And so what is that? 6.4 times 1.6109, and I'm getting 10.31. So in this case, the up and the down are close, but they're not the same. Okay, so let me save that as what? RC practice or something, I don't know. Okay, let me do this so it makes sense. If I put that on the site. Okay. Now let's do the simulation and see what we get. Okay. Again, if you haven't done this, you can't do it for the first time on the test. It takes a little coordination to get used to it. I'm going to turn on, first I'm going to flip the switch down. I want to start discharge. I'm going to I'm going to turn this circuit on. Then I'm going to click into the workspace. So then it will take my space to flip the switch. I'm going to hit the switch, then it's charging. I'm going to hit the switch, then it's discharging. Then I'm going to come and turn the simulation off. Okay, and I didn't show my oscilloscope, but I can show it either during or after. See, there it is. Okay. So at first I ran it without the oscilloscope showing, and then I brought up the oscilloscope, but I can also do it with the oscilloscope sort of showing. So let me do that again with this oscilloscope showing. So turn it on here, click, click, and then off. And now we need to play the game of finding the time constant in simulation. and I'm looking to get into this, what I call the corner. I have 197 micro and it's not changing, and I'm looking for the first time it does change, and then I go back. So now I have this corner, and then I go up to 63% of where I'm heading, and I'm heading to 12. So 0.63 times 12 is 756. So I need this second voltage to be 756. And now I'm close, and then I do, that's 755. That's about as close as I'm going to get. Remember, if this goes up too fast, you play with the time scale. If it goes off screen, you might have to play with the voltage scale. So this is the Y, the voltage, and this is the X, the time. And you may have to play with those scales. In this case, so that I'm doing, I did not have to play with the scale. Okay, so I got the corner and I got the voltage and 63% of my saturation. And then here is this third row down here is doing the subtraction for me, and it is 9.17 millisecond. How did that compare to my calculation? 9.12 milliseconds. So not a bad simulation result compared to the theory result. You've got to prove to me that you know how to get the answer. So it's not good enough just to show me an oscilloscope. You got to put the needles at the corner and the needle at the 63%. And then maybe you want to circle this answer or write it down somewhere to say, I know this is the answer. So just the screen capture is not the answer. You've got to indicate to me that you know what on the screen capture is the answer. The 9170 is the answer. You either retype it or you give a circle in a screen capture or something, some way to indicate I know that's the answer. All right, let's move over to the discharging part. So now I'm looking for it to be going down. Again, I'm going to put the 1 at the corner. So here I am at 11,999, and I'm looking to be in the corner. So there's 1199. I'm looking for it to change. And then it just changed. Now I go back. Okay, so I'm at the corner. And then now I want to go down to 37% of, so 0.37 times the 12. And that's 444. It's 37% of where you start to come down from. Now, I was pretty close to the 12s. I was at 11,999, so I'm using the 12. But if you like really flip the switches fast and you're coming down from, I don't know, 10, then you work with 37% of the 10. You start at the percentage going down is a percentage of where you start. I'm starting close enough to 12 to call it 12, but if you don't let it get up to 12, then you got to work from wherever you start. So I'm looking for 444 for this second needle. Okay, now here I am at 4418. Can I get any closer? Not really. That was probably the best. 4418. Okay, so number 1 is at the corner. Number 2 is at 37% going on down. And then here is, again, the subtraction in row 3 is my time constant, 10.381. How did we do? 10.31. So we did well. Okay, so that is the game. You have to recognize who's involved in the charging circuit and who's involved in the discharging circuit. That's problem 1. You make a path from one side of the battery to the other side of the battery. That determines charging. You make a path from one side of the capacitor to the other side of the capacitor. That's discharging. You figure out who's in series and who's in parallel. You remember that resistors in series and parallel do the opposite of capacitors in series and parallel. you get R equivalent, you get C equivalent, you multiply them, that's the time constant. You do the same thing for discharging. And my God, use your voice. All the capacitors are in the discharging circuit. I never changed the capacitors in my charging or discharging circuit. If I were to change the capacitors, then there would be a sort of, it wouldn't be, there'd be like a discontinuity, and I don't want you to have to deal with that in your analysis. So all the resistors will change, the capacitors and what I'm doing won't change. So yes, it is in the discharging circuit, and the capacitors will it's not like in life that's always true, but in what I will give you on any lab or test, that's true. The capacitors will always, all the capacitors will be in the charging and all the capacitors will be in the discharging. Okay. Anything else? Again, that is a good question to ask. You know, it's going to be the first question and a lot of points on that question in on test 2, which is going to be after Easter and probably not the week after Easter because that's an online week, but probably the week after that. And I'm still, oh, yes. Was somebody asking something? No, all right. You got to know your percentages going up and down. Lots of people will do this, go to the corner and go up here where it's up here where it's flat and tell me that's the time. That's not what a time constant is. That's closer to like 3 time constants or something like that. You've got to play the game as it was told to you. Okay. Any other questions before I go back to talking about semiconductors? But if you had questions on floats or anything like that, adders, subtractors, memory. He's still chatting with me. Okay. How is R2 and 3 in series with 4? Okay. So it's not individually, but that combination, the R2, R3 combination. So when the switch is up, current comes out of the battery. Some of it goes to 3, some of it goes to 2. That's what makes them parallel. And then, but all that current recombines, goes through the switch, and then all that current goes through R4. So that makes that combination in series with R4. That is our definition of series, that they see the same current. When we talk about capacitors, we talk about something similar, that they see the same charge. So some charge comes onto the charge that was coming out. So the current that I was talking about is a bunch of charges. Current is just charge changing in time. But so there had to be, for there to be a current, there had to be charges moving. And what happens to those charges after they get through R4? Some of them go to C1, and some of them end up on C2. We usually talk about positive charges. So those positive charges leave the battery. Some of the positive charges go through 3, some of them go through 2, but they get back together. So 2 and 3 were in parallel. Then all the charges go through the switch, and all the charges go through R4, and then they split up again. And some of those charges go to the C1, and some of them go to C2. Now, what happens with a capacitor is those charges are stuck there, but they send other sort of proxy charges out on the other side. So the positive charges land here, and they send out the same amount of positive charges down here. And the same thing over here with 2. And so the charge split up here at this junction, and some of it went to 1 and some of it went to 2. But then those two recombine. So that makes C1 and C2 in parallel. And all that charge recombined goes through 3. So that's why C1 and C2, that parallel combination, is then in series with 3. Okay. So in the resistors, we make the discussion about current, and in the capacitors, we make the discussion about charge. I could do this. Let me rotate this guy back counterclockwise. I could do this, which would drive you nuts. They are still in parallel. Parallel is not, do I look at them geometrically and they look like they are in parallel geometrically? Electronics does not give a rat's ass about how things look. It's how they are connected. So it is about this junction on before you get to the capacitors and this junction after you get to the capacitors. That's what makes them parallel. It's got nothing to do with what they appear like visually. So don't fall for any silly little things like that. Any questions, more questions on this, or any other question? And I'm fine if you fill the day with questions. All right. My questioner is not questioning me anymore, and nobody else is questioning me. Okay. All right. So let me, if you're not going to ask me questions, then I will go back to talking about, I'm going to make a new, just no, new. All right, so what was I blathering on about on Monday? Semiconductors and doping. Okay, so let's remind you, we had this energy picture of an atom. There's a way of looking at the energy of an atom. And so we just say that so this is the energy axis, and we say that they're just certain energies you're allowed to have. Sometimes there might be 2 that are the same or close by, but that's the way energies are in atoms. And then when we brought them a bunch of atoms together, so this was an atom. And then if we bring, I'll call it here, a bunch of atoms together, I'll call it a material. Then there's some left over here, and that I'm just going to draw it very sloppily. But this sort of fills in a bit and makes what we call a band. And then this sort of fills in and makes up a band. And then when we talk about atoms, we fill the atoms with electrons. So here's an electron with a spin up, and here's an electron with a spin down. So we can, some people will draw the arrow up and the arrow down for this so-called spin. And that's the idea of like what makes the periodic table the way it is. And the patterns in the periodic table are the patterns that the electrons have in the outer shells. And then when we have the material, we do the same thing, filling this up. Let me change my color. So I fill this up with these electrons. And then we have a similar question of the nature of the material is going to be determined by how the sort of last filling. So we fill it up. So atoms are determined by their valence electrons, by the electrons on the outside, and materials are similar, that they are determined by where do we stop filling up with atoms. Okay, so the valence electrons matter. That's what chemistry tells us, the valence electrons. What are the orbits of the valence electrons and how many electrons are on the outside? That determines your main chemistry. What determines your main material nature is similar. You're filling up a band. This is a band. Remember our vocabulary. And this is a gap. And then we're filling up with electrons. And then it matters, are we in a band when we finish filling, or are we at the top of a band where we're sort of more determined, our behavior is determined by the gap that we're sort of at the gap. Are we within a band or are we at the gap? That's what will determine our properties. If in the filling up, we're in the band, well within the band, in the middle of the band, then we are a metal. And if we're near the top of the band, then we are a semiconductor or maybe an insulator. Depends how big the gap is. Okay, so that's just a quick fill in of our picture. And then we introduce this analogy instead. So save I don't know, orbit band review. Okay. And then we had this analogy we were talking about of classes. And I usually end up teaching this at registration time, so it just falls in nicely. Okay. So we have courses, we have 100 level courses, 200 level courses. Those are like the bands. And so 100 level courses have a certain level of difficulty. They're not all the same level of difficulty, but they're all close. And then the 200 level is more difficult. So there's a change in the level of difficulty. That is our gap. The change in the level of difficulty is our gap. And then we have the 200 level courses. So there's a gap in the level of difficulty, gap in difficulty. Okay. I'd love to be able to write on a board, maybe in the fall. All right, so we have this gap in the level of difficulty. The seating in these courses is fixed. So we have so many courses at the 100 level, so many seats in each course, and then the students are filling those seats. So I can never remember the numbers I choose. Let's say I have 100 students, and they're going to take 4 courses each. And then let's say I have 10 courses, 10 100 level courses with 20 seats each. 20 seats each, okay. And the same for 200. Okay. Again, so this is an occupancy thing. We fill these seats. So I have 10 courses, 10 100 level courses with 20 seats each. So that's 200 100 level seats. And then people start registering and I fill those seats. Again, there are no specifics in the core other than you need to take courses. So, you know, it's not you're required to take a 300 level course or anything like that. You just take courses. So, of course, the students who register early, they take the fun, easy courses. And so the first 50 students taking their 4 courses fill up the 100 level. And then those who had holds on their account or whatever and have to register later, they're going to fill, I'm going to say I have the same number of 200 level courses, 10 200 level courses. So let me just say ditto and 200 level and ditto 220 seats each. So I have my 100 students taking 4 courses. So I have 400 seats I need. I have in my 100 level, I have 10 courses with 20 seats each. And that takes up 200 of the seats. And then the other level takes up 200 of the seats. And so when registration is done, everybody's in 100 or 200 level courses. Nobody's in 300 level courses. So nobody in 300 level courses. All right. Nobody's taking the 300 level course. Everybody's taking 100 level course, the 200 level course. Nobody takes 300 level courses. And that's what makes us semiconducting, in that there's not any easy freedom. If you want, for whatever reason, you want a little bit of freedom, you want to change your schedule. I always use the example of like there's an afternoon job that you'd like to pick up or something like that. If you want a little freedom in your schedule, there's no freedom in your schedule. The next available course is a 300 level course. You have to jump the gap. You have to take a significantly more difficult course, the 300 level course, to get that freedom in your flexibility in your schedule to be able to take the afternoon job. And to be able to conduct for the real system, to be able to conduct, for the electrons to be able to move around, that's that bit of freedom I'm talking about. So so I'm just going to call it freedom in my analogy. Freedom of scheduling means you have to jump the gap, which is to take the 300 level course. Okay, that's semiconducting. There's not much freedom of movement because of the requirement of jumping the gap to get the freedom. Okay, and that's, we got a little bit further, I think. Okay, because I started to talk about doping. Okay. So call it band analogy. Okay. Then I said I had a program for international students or something. Okay. So I have this international student program. Oh my God, program. And they take It's not everybody, but it's some of my students, and they take 3 courses a semester. 3 courses. All right, I curse all you people who need to stay at home. All right, so they are taking 3 courses. This is just some of my students, some students. Some students are in this international program. They're taking 3 courses, and I don't know, they're traveling, they're learning the language, whatever. They're taking 3 of my courses. Now my courses don't fill up. I have the 100 level. They're probably still all full, but I'm not having 100 students take 4 courses. I'm having 80 students take 4 courses and 20 students taking 3 courses. That doesn't fill up my 200 level. So my 200 level is no longer full. 200 level is not full. Okay. With my 200 level courses not full, now if I have the situation where there's somebody wants the afternoon job, somebody can get the afternoon job. It's not, there's flexibility in the schedule, at least the people who are taking the 200 level courses. The people who are taking the 100 level courses, they're not going to budge. They've got an easy schedule, they're going to keep it. But the people who have the 200 level courses, there are nearby 200 level courses that are just a smidge more difficult. And for the freedom, they'll go into those courses. So they have freedom, they have mobility. In the real system, they can conduct. So we can conduct. So doping makes conduction better. Does it make you as good as gold? Gold's a very good metal. No, it makes you better than you were. It doesn't make you good. All right. Okay, so this is known as P doping. And in P doping, I have less things that are filling my level, and I get a little bit of freedom in my what's called the band that's full is known as valence, and the band that's empty is known as conducting. So the valence band was full before, and the conduction was empty. What's called the conduction band is empty. And then in P doping, change my pen, it's no longer full, it's just near full. But being near full means there's some flexibility, some ability to conduct. So that is my analogy for P doping. You have less requirement for seats, and because fewer students are taking 4 courses. Now let me show you why did I say 4 courses. That was not an accident. So what do I want to say? A periodic table. I just want a picture of a periodic table. Good enough. Okay. So the let me make it bigger. Okay. The semiconductors are here in the things that have 4 things in the outer shell, like Silicon Valley, semiconductors, you know this, okay. So you start over here, you had 1 thing outer, 1 thing outer, 2 things outer, 3 things outer, 4 things outer. So carbon, silicon, germanium, these are things that have 4 in the outer shell. If I come along and use aluminum, instead of having all silicon, I use a little bit of aluminum. It's similar in size, but it's got 3 things on the outside rather than 4 things on the outside. That means I have some empty slots. And that means I have, if I sprinkle in a little bit of aluminum, I have some empty slots in my valence band and I can conduct. That's p doping. Okay. Any questions? So that was p doping. Now I'm going to do something called n doping by analogy. Okay. I'm at now a completely different university that's across town. But I had the similar situation. I had the 100 level courses, 200 level courses, they were completely full. And I had nobody taking my 300 level courses. In this university, I have an accelerated program. These are people who want to finish early. And so they're going to take 5 courses. That is a 5. Doesn't look the hell like a 5, but 5. So again, this is not all my students, just a set of my students take 5 courses. So instead of having 100 students taking 4 courses, that's 800 seats, that filled my 100 and 200 exactly. Now I have, I don't know, 20 of my students who are in this accelerated program, and they take 5 courses. So now I have, what do I have? I have 120 seats that I need because 20 of my students are taking an extra course. And so now I have, in this example where I said the word is 20, I have 20 students taking 300 level courses. So I have some students, I'll just say Stu, taking 300 level. What does it mean in the real thing? Some electrons in conduction band. That's the analogy is some students taking 300 level courses. The real thing is some electrons in the conduction band. That gives me my freedom again. Who can take, if the afternoon job comes around, who's got the freedom to take it? Why, those students who are taking the 300 level course. They can take a slightly more difficult 300 level course, only a smidge harder, and they have the freedom to take the job. So they have those electrons in the conduction band, have some freedom, give me some conduction. Okay. And this is known as N doping. Let me go back to the periodic table. This is if I took silicon and I sprinkled in a little bit of phosphorus. Phosphorus has 5 things on the outside, 1 more than silicon. And so there's sort of some extra things on the outside to deal with. And so those extra things go up into that higher band. And so those things in the higher band, they have the freedom because they can go to just a slightly higher band, a slightly higher energy level than they're already in. And then, but they can move. Okay, So we took something that didn't conduct, something where to move, you'd have to jump the gap, something where conduction was hard, and we can N-dope it and we can make it better, or we can P-dope it and we can make it better. But again, we are making it better, we are not making it good. You make it better, you don't make it good. So why, if you're just gonna have a semiconductor and you're trying to make it a conductor, then to hell with it, just use copper or silver or gold or some metal. You don't, if you're trying to make a conductor, you don't start with a semiconductor. But we're not trying to make a conductor. That's not what we're trying to do. Now I'm going to do something that makes no sense. Okay. So this was N-doping. Let me save that. Okay. Now what am I going to do? Something crazy. I'm going to take this semiconductor and I'm going to have a P-dope side. And then I'm going to have an N-dope side. Okay. This is known as a P-N junction, where the P and the N come together. Okay, so I have P's and N's coming together. What did my P look like? I had full level here and some slots. I had some empty slots here in my valence band. And what did the N-dope look like? That's the P. What did the N look like? This was full, and I had some guys up here in the conduction. So this is the valence. This is the conduction band. And P had, this had some slots, and this in N, this was full. And then we had some people up in the conduction. So what would you do? Okay, you are at the N-doping university, the one with the accelerated program, and you're taking these 300 level courses. You're one of the people stuck taking the 300 level course. And across the city, there is this P-dope university, and they have open seats in their 200 level course. What are you going to do? You're going to see if you can transfer credits from the other university and take an easier course. So that's what you want to do. So you'd like to go over here and take that easier course. But there's some penalty for that. Now, I talked about you often hear people talk about N-doping as having extra electrons, or P-doping as having fewer electrons, but they are neutral. I didn't sort of have silicon and I stole some electrons from it. I brought in aluminum, and aluminum's neutral and silicon's neutral. Aluminum just has to have fewer electrons on the outside. And on this side, I had the silicon with phosphorus. And again, phosphorus is a neutral thing. It just has more electrons on the outside than does silicon. But if I start taking electrons from my N-dope side and putting them over into my P-dope side, I'm getting an honest to God charge separation. I was neutral, but I'm taking charges from one side to the other. That is a separation of charge. That always costs energy. So this is a charge separation. Charge separation. All right. And charge separations cost something. So there's something to be gained. These electrons are in a lower state, and that's nice, and it's an easier course in the analogy. But there's some penalty to be paid. There's a charge separation. So there's some penalty to be paid for the student. Let's make it up. There's a fee to transfer credits, or you've got to commute on the bus. There's some penalty. It's in the real system, it's like a charge separation. Okay. And now, but what also happened was I lost my flexibility. I had the semiconductor, it had no flexibility. I p doped it, I gained some flexibility. I n doped it, I gained some flexibility. I put the p's next to the n's, and I lost my flexibility. Why in the hell would I do that? I did all this work, all this doping to gain flexibility, and then I put the p's and the n's next to each other and lost my flexibility. Why, oh, why would I do that? Okay. So this is the, okay, I didn't save it. Oh, well, what the hell? It's on the video. Okay. Now I'm going to say I have a charge separation. I'm going to say that's kind of like, so here's, go back to black. Here was my P, and here was my N. And what happened, sorry, is with my electrons is then the electrons jumped over here. So this side has some negatives, and over here I'm left with some positives. Okay, so I have this charge separation. I'm not going to continue to get all of my all of my accelerated students aren't going to go to this university, but some of them will. Some of them will pay the penalty, but not all of them. Okay. Because it gets harder and harder as these sort of fill up. Okay, you get more and more charge separation. It's a bit like a capacitor. So it's like a capacitor. Because a capacitor is where the other place where we see a charge separation. Okay, now let me connect this thing to a battery. Let's put that in blue, why not? So here's a battery. I'm going to have the long ends like this at first. Okay, so I'm going to connect my long ends, which where positive charges come out, and I'm going to connect them to this PN junction. And here's positive charges come this way from my battery. And what happens? They come and they meet these other positive charges that form at the PN junction. And so these charges meet up with these charges and they make it worse. So these positive charges come around and they make it worse. So I have a charge separation that costs me energy. If I connect the battery to it this way, I make the situation that's already bad worse. So I had a good conductor. I had a so-so conductor. I doped it. I made it better by P. I made it better by N. I brought the P and the N together. I made it bad again. And now I've connected a battery to it and made it worse. This is known as reverse bias. In this direction, the battery makes the PN junction worse, a worse conductor or a bigger resistance. I'm going to draw another picture where I'm going to turn the battery around the other way. So this is, try to save it. This is reverse bias. Okay. Again, I have the P, and I have the N, and I was drawing this ended up with some extra electrons. This ended up with some extra positive charges. I'm going to connect my battery the other way. So this way, the battery sends its positive charges out. I better make a complete circuit or you'll yell at me. And now the positives meet up with the negatives. And that makes it better. So the positives are coming in here and they make it better. And so I have a situation that's not a good conductor. It's got resistance. But when I connect the battery to it in this direction, it makes it better. It makes it more conducting. It's taking that problem that the junction made and sort of alleviating it. And so this is known as forward bias. And it makes the situation better in terms of conducting. Okay, so what have I gained? I took something that was not a good conductor, a semiconductor. I doped it. I made it better by p doping it. I also doped it with n and made it better by n doping. But I brought the p and the n together, and they made it worse again. But I gained directionality in that going in one direction is good and makes it more conducting, and going in the opposite direction makes it worse and makes it less conducting. We've never had anything like that before. The resistance before was always, the resistance of the resistor was always the same. Now we've got resistance changing. So it changes with direction. It also is non-linear in that it's really hard to get it going. And then once it gets going, the resistance really drops. So the resistance is going to be a function of the voltage. Before it was a constant, before it didn't change, now it changes. That's going to give us a sense of sort of on and off. And we also have directionality, so that we have something that prevents current from flowing in one direction, allows it to flow in one direction, and prevents it from flowing in the opposite direction. And so this is a new device known as a diode. Okay, so p-n junctions make diodes. I call it in the slideshow, which is now a video on YouTube, I make an analogy that it's like a capacitor. But if I ask some question, what is another, what gives you a p-n junction, another name for a p-n junction? The answer is not a little capacitor. The answer is diode. So diode and p-n junctions go together. Capacitor is just part of my explanation, okay, not part of the answer to any important question I might put on the test. Okay. So now, do you have to do this on a test to go through all this argument? No. You have to know what forward and reverse bias is. As a circuit element, diodes look like this. And you just think of the ones, think of that triangle as an arrow. That's the direction it wants to go in. And so it wants to flow along. We always talk about positive charge. So it wants to flow, positive charge wants to flow in the direction of the arrow, doesn't want to go in the opposite direction. So we get directionality. This is important for us in that the power that comes to us from the power stations far away comes to us in alternating current, which is going back and forth, a sine wave. It's oscillating. But in our computers, we only want one direction. We want DC. So we want to go from AC to DC. And these diodes are going to help us do that. So they're going to play a role inside the computer, but they also play a role of getting power in the right form to be used by a computer. And I think I'm out of words unless there are any questions you want. Okay, I'm going to stop recording, I'll stop sharing, check my attendance, and then hang out for any questions people have.